Our next speaker is Omar Allahar. I will not spend time doing introductions because we are very late. Thank you, Omar. Would you like
I have one here.
Okay.
Hello, yeah. Yeah, before I start, I just want to reiterate thanking CDB, William, and Antonio and team. They have supported the CRG for a long time. Call William for anything, and he never hesitates to help. You have to excuse me, I'm a little nervous this afternoon. I wasn't nervous earlier, it's nothing to do with y'all. Tony McNichols at lunchtime told me he came here specifically this afternoon to laugh at me, which I don't think was very nice, but these offshore engineers, you know, they're a bit. That video you're seeing up there was on YouTube, so I took it down. It said it was 120 mile an hour Cat 3 hurricane. I think that fella's a bit of a Johnny, but yeah, so I put that up because we talk a lot about wind speeds and we come here and talk, but you never see the actual thing and what it looks like. If anybody's ever been in a hurricane themselves, they would have had a similar experience. I have a do-flicky thing here. Yeah. Right, just to make sure you're paying attention. The students, where's that quote from? Very good, and who said it? Who said it in Animal Farm? Anyone? Okay. Napoleon, but not Napoleon Bonaparte, Napoleon the pig, right? The point is that this is the same thing with wind speeds. All wind speeds are not equal. Now, this is a very simple presentation. I'll go through pretty quickly. You wouldn't believe it, but I had a case in Barbados where somebody had a solar farm. They were about to build it, and they came at the last minute and said, would you check the solar farm first, because we're not too sure if the racking was done properly. And when I looked at the calculations from the engineer abroad, I wouldn't say from where, they are designed to 150 kilometers an hour, which is about 90 miles an hour. And I pointed out to the client straight away, and he said, but I told them to do it for 150. So yeah, but they did it for 150, 150 kilometers an hour, totally undesigned for the Caribbean. So we have to know what units we're talking about. The period of measurement of the wind, whether it's in seconds, minutes, our average, is important. The next thing is the elevation. The higher up you go, the higher the wind speed. So we tend to quote some of the wind speeds we were talking about this week is at 10 meters. In wind turbine design, it's not, it's at hub height. We have to look at the factors of safety. What factors of safety are you using? I'll go on to this a little bit more in a second, and that could be quite controversial as well. But we have to recognize that without all of these factors, the wind speed is meaningless. Somebody could come and tell you 150 and you don't know what they're talking about. The wind code we designed in the Caribbean, with the Caribbean wind maps that you saw earlier, is the ASC 7 2022. And somebody was asking yesterday about the regulatory body here not being updated, but I myself just bought that about a year ago. It's not freely available online, costs like 350 US. But wind turbine designers use the International Electrotechnical Commission 64100. This is not a document that structural engineers would be familiar with. And my talk today is all about how these things compare, how the wind speeds we designed to and the wind speeds they designed to are not comparable in effect. And we will go on to see more of that now. So the main issue, sorry, that's a picture of the Hurricane Milton the other day from the Dragon Endeavour. I thought it was kind of cool, so I put it up there. The fellas, those were the guys that were going up to rescue the other astronauts that were stuck. I can't imagine telling my wife and my girlfriends that I go into space for 8 days and then get stuck for 10 months or something. That would be in real trouble. Yeah. You could read that if you want, but the long and short of it is that if you don't understand how the ASC code and the IEC code compare, you will probably specify the wrong wind turbines for your projects, and you'll come out with a bad result, right? So that one says the same thing in a different way: improper siting, incorrect turbine specification, etc. What's next? Right, a table that you guys should all know. This is from the IBC, and just to confuse you, we talk about categories and classes, and they're all interchangeable, but IBC talks about risk category buildings. Category 1 being a temporary structure, like the contractor, Matthew was his name, that was talking about designing yesterday, Mr. Gibbs not having invoiced him. Don't worry, Mr. Gibbs, I'll invoice him for you. Category 2 falls in between category 3. It's not listed here. It's a funny category. Category 3 is what we design power plants to and considered substantial hazard to life building. You can understand why a power plant would be that, because if you lose power, hospitals and, and category 4 is critical building facilities like police stations, airports, hospitals, etc. Funny enough, in the wind turbine world, they design everything to a risk category 2 structure. That's just how they do it internationally. We disagree with that at the CRG. We think that because we are now going to a world of 100% renewable energy in the Caribbean, in islands like Barbados, that I'm sure William will help Barbados get to full 100% renewable energy by 2030, as the Prime Minister has requested of him. We need to make sure that our renewable energy infrastructure is resilient, which means minimum Cat 3. If you have a solar farm connected to a hospital, it needs to be a Category 4 structure. That's an extract from the same wind maps we were talking about yesterday. I'm just doing the Barbados in the Eastern Caribbean, or in Barbados as they call them, the lower islands. So we do have the maps to apply to the ASC code. And in the IEC now, this gets a little more specific. They have different classes of wind turbine, to just confuse you again with classes and categories. And so there's a class 3, 2, 1 wind turbine. And there's a new class, a class T, a tropical class. And basically what they do is, in manufacturing and machinery, they can't design bespoke for every project. So they design 3 standard turbines, and you come and get that one off the shelf. I know what my site is, I'll have one of those. There's little things you could do, foundations, different and all that sort of thing, but it's very difficult. Nobody's going to manufacture a turbine for you for your specific site. And that's part of the big challenge we have in the Caribbean. Most of these turbines are designed for use in non-cyclone zones. So in the last IEC 2019, they added in a tropical wind turbine for us, but then they went on to say that actually that doesn't mean it's designed for hurricane zones. So yeah, just to point out, the wind speeds they have here are meters per second at hub height. Now you get wind turbines at different heights. It could be 80 meters, 100 meters, 130 meters, but that is always at the hub height. right? And the wind speed average is over 10 minutes, not 3-second gusts that we use in the ASCE, right? So all these things are. There is a class S turbine, which is a site-specific or special turbine. And this is a quote from the IEC here that says, Class T does not cover all areas prone to tropical cyclones. A site-specific assessment is required. So they go on to put a tropical one in there and then tell us we can't use it. I put a few pretty pictures in there, but they don't mean anything. The main difference, and this is the key thing here, the main difference between the ASC and the IEC is the ASC's ultimate wind loads ever since 2010, Mr. Gibbs? Yeah, ever since 2010, we went from service load to ultimate wind loads, and it's at 10 elevation at 10 meters. The IEC wind loads that you see for the turbines are service loads unfactored. So again, not comparable, and they are at hub height. So first we have to recognize that the V in the ASC and the VE, which is extreme, in the IEC are not equal or compatible. We are going to do a little bit of an analysis now because you're all engineers. I thought I'd give you a few equations. And it is important to note that you can use a gust factor of 0.85 in your calculations because of the type of analysis they do for wind turbines. And we are going to consider a straightforward calculation here. When I show it, Tony will know it right away. Tony McNichols is, yeah. But what we're going to do is try to convert the wind speeds. We're going to try and use the wind speeds in ASCE that we have with our maps, which are currently in miles per hour and at 10 meters in 3 seconds, and convert the wind speeds from the wind turbines that I showed you in the table before to see how that, because everybody asks me all the time, oh, what does that mean? That class 1 wind turbine, what sort of hurricane will it stand up to? And I've looked everywhere and I can't find it. So I did it for myself, and so now I can answer what we would consider a layman's question, if you would allow me that. Aha, students look away. If you are scarred by fluid dynamics as I was, yeah, you guys could leave the room now, yeah. Don't worry. But it's not that difficult an equation. A half density by velocity squared, and density in this case is the air density we're using. That's a standard air density they use in most calculations for wind turbines, but just note that that's not the air density in the Caribbean. Air density in the Caribbean is a little bit less, is 1.16. There was a study done between Piarco and Pigeon Point actually, which is quite good, that picked up. Right, so now we can compare the equation that we use in ASC and that equation for velocity there that is used in the IEC. Now, what we have to note here, I'll just flick through the factors quick because that's not really important. You can get all of that in the code, the different factors. We're going to use 1 for most of these. No topographical speed up, which is important, and we'll discuss a little bit more later because the reality is that we'll always have some of that. But, and direction factor. But this is the big one. They're using a factor of safety, what they call a power load factor, just to confuse us even more with these terminologies, and we call a wind load factor in structural engineering. They're using a power load factor of 1.35. Now, we could argue about this after, but they have a logic to it. They say that they understand the wind better than structural engineers, and they are doing a better analysis from different directions, although this factor is on the wind load. So really and truly, you should be having, I think, a higher factor of safety because wind load is harder to predict than most things. Of course, you have your material factors of safety and all of that in there already. We use 1.6 in our wind speeds, which is already built into the wind speeds maps that we have. It didn't used to be before 2010. There was a study done in St. Lucia, Peter Vickery and Engineer Tony Gibbs, Professor Gibbs. And the results of the study were that because of climate change, we're getting more occurrences of stronger hurricanes. And until such time as we update the wind codes for the Caribbean, we should, for class 3 buildings, multiply by 10%, and for anything less, 12 to 14%. So I've done that for you guys and created a table in meters per second so that you cannot check me back for some islands in the Caribbean. Now this is straight from, this is the ASC basic wind speeds converted with the additional climate change factor. Everybody's going to ask me, what does that mean for hurricanes? What kind of hurricanes? And this is the table here for every island. The red is category 3 risk structures, and the blue is category 2 risk structures. You see it's slightly less. I didn't do 4 and 1. That's a Cat 1 hurricane there. That's a Cat 2 hurricane. Cat 3. Cat 4. Should I go on? Cat 5. So you can see here that for category 3 structures, almost all of those islands, well, every one of those islands, you have to design for over a Cat 5 hurricane. That's what we use, including our factors of safety, etc. 3-second gusts at 10 meters. Category 2, which some islands you might get away, it's less than Cat 5, but definitely more than Cat 4. And you'll also notice here that the further south you go in the Caribbean, the less the wind speeds increase away from the equator. So what we're going to do is convert the design wind speeds that the IEC has given us for different wind turbine classes and convert it back to something that we recognize a little bit better. And we're going to use the power law equation, which is just an equation that allows you to vary the height. So if it was at 100 meters, I can bring it down to 10 meters. It's, the higher you go, the higher the wind speed. So we'll use that equation in a second. I'm sure you're all very familiar with this equation. I reoriented the pressure equation that we looked at earlier. And you'll notice that I put the ASC 7 wind speeds divided by the square root of 1.6, because that's how we get rid of our factor of safety and get it back to a non-factored amount. Because if we want to compare apples with apples, we want to compare them as a service load. Right, so these are the loads unfactored, the wind speed, sorry, unfactored. Back to the same table we had before, just unfactoring them. And we want to know how that compares to the wind turbine classes, and this is how it compares to the wind turbine classes. So you can see here, I haven't looked at everyone individually, but the class T wind turbine, for example, at 10 meters 3-second gusts is a 62 meter a second wind speed, design wind speed. That's what's designed for. We're not taking topography and siting into account just yet. But you look down category 3 structures and 62 So you get up to about Guadeloupe and you're kind of okay. And then anything above Guadeloupe, a Class T wind turbine can't work if you're designing for a category risk structure 3. But as I said to you before, they tend to do it as a category risk 2 structure. So you would see that 62, you might get an extra island in there or something. But even then, it's sort of marginal. Again, please note, there's no topographical speed up in these numbers, so it could get worse. And these numbers, our wind speeds on the wind maps in ASCE are on land, as opposed to the wind speeds for hurricanes, which are at sea, and 1 minute average. I hope you're all paying attention, right? Because it's fairly simple, but it's just all of these different averages, different heights. It's sort of all over the place. So it's difficult to compare apples with apples. And that's why I had to do this calculation for you guys to show you. So if you're a different exposure class, again, close to the coast, Class D, you'll have other factors you have to put in it. If you have is on the edge of a hill, topographic factors will come in, etc. I'm trying to do it as a fairly standard comparison. What category hurricane? Again, people always ask. What category hurricanes are these standard class wind turbines designed for? And category 3, now you will see the gust speed over land. Tony Gibbs showed this table yesterday. It's an extract from the ASCE in the commentary section. They themselves always get asked the same question. So they have converted the hurricane wind speeds 1 minute average over open water to gust wind 3 seconds over open water in the next 2 columns, and then gust over land 3 seconds. When the hurricane hits land, it slows down. Friction on the land slows down the wind speeds. It actually slows down closer to the coast because over open water it's assumed that the sea is relatively flat, almost smooth, because the wind is blowing everything across. As it approaches land and the water gets shallower, the waves start to get choppier and they start to get some friction, so the hurricane starts to slow down, and by the time it hits open land, it slowed down even more. So there's about 3 different zones in there. But we just assume that it's hit land here, and that's the wind speed over land. So the next turbine, a Class 1 turbine, could probably survive a Category 2 hurricane, and a Class 2 turbine might just be able to survive a Category 1 hurricane, a high Category 1 hurricane. All the numbers I'm doing here, I've assumed 100 meters hub height and pull it down just for the purpose of this talk. That's Trinidad. I stuck that one in this morning quick because we in Trinidad, yeah. Yeah, and I know Tony was going to come and ask difficult questions. Yeah. So please ignore all the miles per hour. Hold on a second. I did that to confuse you. In Trinidad, those are the wind speeds, including climate change factor, that we are supposed to be designing for. This is a Category 3 building, a risk Category 3 building. So in the north, and you can see as you go further south, it reduces. Same thing in the Caribbean. Further south you come in the Caribbean, the wind speeds get less, and vice versa. In the north of the island, this is all on land. We're not talking offshore. A Class T turbine may work there. Further down, where's that, Rima? That's quite a Rima yet. Central, Chaguanas. Chaguanas, a Class 1 turbine may be able to work. And if you go even deeper south, same Class 1. And right in the heart of the Baluba, a Class 2 wind turbine might be able to work. You have to check the site, you have to check the topography, and so on. And that's it for me. I have one small video to show you what happens when you get it wrong. But I'll just wrap up with a quick conclusion. So please note that the wind speeds that are in the IEC and the wind speeds that are in ASC are not comparable. They are completely different. Topography. Topography plays a big factor in it. The picture that's behind is Marigala just off the coast of Martinique. And you can see the wind turbines on the ridge. So topography will have a big effect there. It will have a speed up. That calculation in itself needs to be done for every site. I can't come and say which turbine will go where because you have to, it's very site specific. Some class 1 and class T turbines may meet structural risk category 1 and 2 requirements in the Caribbean. In certain places, again, all site specific, it all has to be checked. You all have to hire me. Wind turbines designed for the Caribbean need to be site-specific design and will mostly require a Class S design. Class S is the site-specific. And what they do with the Class S, which is funny, they just take a Class T. They don't redesign the nacelle or the hubs or the blades. They might give you a shorter tower, stronger tower, and they do bigger foundations and that kind of thing. But again, they're not going to manufacture and design a turbine specific for you for the region. So going 100% renewable energy might be difficult. This is what happens. There's Hurricane Hagi, Typhoon Hagi in Japan 2 months ago. Sorry, it had some nice music, but I don't know why it's not playing. Those were turbines designed for hurricanes, right? That's multi-millions of dollars in turbines. That was a Category 4 typhoon, just over Cat 4. The good news is they have other wind farms in the area that survived. That one didn't do too well. Thank you very much.
Do we have any questions for Omar? Yes, okay, Kunal. Ask difficult questions, okay? He could handle it.
All right, this one is easy. There was a newspaper article in Barbados a couple weeks ago, Sunday Sun, where it was reported that some wind turbines were imported into the island for erection in the north of the country. The author raised concern about the suitability of the turbines for our design wind speeds. Do you have any idea about that project here, and if those turbines would have been, as I now learned, Class S? And if they weren't, how easy is it to retrofit them so that they meet the Class S standard for Barbados?
I am not the engineer on the project. Let me first state that clearly. I saw the article as well, and it's on the internet. There's a company that says they're refurbishing these 12 wind turbines that were in the south of France. They're over 20 years old. From what I could see, they're Class 2 wind turbines. So they're definitely not designed for Barbados conditions. A class 2,
Based on your conversion there, class 2 puts you at what design wind speed?
about a high cat 1, low cat 2, you know, depending on what, yeah. So definitely not designed for Barbados. The part of France where they say they're bringing them from a place called Upia, the design wind speed there is 90 miles an hour, 3-second gust. The design wind speed in Barbados is 165 miles an hour, 3-second gust. So there's no comparison. But even further to that, when a machine like a wind turbine has been operating in the field for over 20 years, in order to reuse it somewhere, you have to do a full reanalysis of the turbine because the turbine mast moves and it gets strain and stresses and strains in the turbine, in the steel building up. So you have to do a whole reclassification of it again, and it would be even downgraded more than it was when it was brand new. So I don't know how they're letting that happen in Barbados, but that's above my pay grade.
Well, how easy would it be if they to retrofit them locally? Is it something that could be done? As you mentioned earlier, you shorten the tower and it gets a higher rating?
Yeah, it's not so easy. You see, the reason why they do these turbines like this, they have a certification process they have to go through. So when you design a new turbine, it has to be tested, and they spend a year or two doing tests and measurements and all that. And then, like in the European Union, somebody will come through and certify that a turbine does what it says it does. So if you go and change the design of a turbine, use a different tower on it, or cut off an existing tower and lower it, it loses its certification. So you have to recertify that turbine again and put it through its paces again before you can use it. So yeah, it's difficult. Hello?
Yeah, Omar, maybe you expecting a difficult question from Tony, but here I am. There is a lot of rain involved in a hurricane, apart from the wind. And as we know from cable bridge designs, rain affects a lot the structure. Is that taken into account for the hurricanes when we are designing a wind turbine, the rain, I mean?
No, it's not really taken into account design. The machines are designed to be out in the open. They're covered. They have a housing that covers the nacelle, and I have a little video that shows the inners of a wind turbine, which is quite cool, like a flying through the wind turbine. But all the machinery inside there is basically outdoor machinery, and accustomed to and designed to take water.
I'm not talking about the machinery. I'm
talking
talking
about the tower?
The tower itself, the structure.
Yeah, no, the tower has drain
or
holes
or the blades, or.
Oh no, yeah, but the blades are fiberglass. You know, it's sort of the construction is all sort of offshore, resilient construction. It could get wet, and be all right. You're talking about in a hurricane, particularly?
No, I'm talking about the oscillation that it might be created because of the rain effect on
okay.
the structure.
No. They do take that into account a little bit in calculations for the wind, not so much the rain, but the wind turbines tend to shut down at 25 meters a second, and the ones that are designed for hurricane resistance. A company called Vestas does one that they put up in Martinique, in Grand Riviere, not Grand Riviere Trinidad, Grand Riviere in Martinique. They actually turn the hub can yaw and move into the hurricane all the time. So the blades flatten and it moves into the hurricane all the time. So it's always facing the wind, because what you don't want is the hurricane blowing on the side of the turbine. So that way they make it. It turns off completely, so it's not spinning or generating, but the only thing that's working is that, we get these hurricanes, they pass over, it's 3-4 hours, hard lash, and then the next day is only mosquitoes. Yeah.
Omar? Yeah, I think part of the question you just answered, but have you looked at the operating speeds for the turbines when you're classing the turbines? the design speed you're using, that's the storm loads that you're designing for. But you would only see the storm loads if a storm is coming, a storm approach. But if you're doing a site-specific design, then are you looking at the site-specific operating normal 1 year return wind speeds to design your turbines?
Yeah, good question, Tony, as usual. It was on the table that I showed from the IEC, actually. So a class 3 turbine is designed for an average year-round wind speed of 6.5 meters a second at hub height, 10 minute. Class 2 is 7.5, and a class 1 turbine is 8.5. Is that right?
Yeah.
I think it's 7, 8.5, and 9.5 actually. And so they're saying that if a turbine goes somewhere where it has generally strong winds consistently all year round, we put a class 1 because it's stronger, it has stronger blades, it has shorter blades, and so it can put up with that sort of beating more consistently. But that might be somewhere that doesn't have hurricanes, just good wind all the time.
Yeah, so I guess what I get into there is, could you spec a lower class turbine in a hurricane zone if you take mitigations to prevent the turbine from even seeing the hurricane loads?
Right, so we just finished a project in Barbados with a special turbine that turns down. It's a smaller turbine because to turn a turbine is 55 meters to 180 foot in the air. And to turn it down is not so easy. So there's a smaller turbine, it's 275 kilowatt turbine. 4 of them make up a megawatt. But it takes up about the same amount of land as if you had 1 megawatt turbine there. And those turn down, the blade strapped down. I actually had a picture on there on the side, me walking past one. And yeah, those are, I don't want to say category 5 proof, I say resilient, because that's on a dairy farm and a cow might fly through the air or something and hit it. So you never know. But yeah, that's the only way I know to say for sure that it wouldn't. Yeah.
Thank you, Omar. You and your flying cows. Appreciate it.